We have left it that our test statistic is 1.43, which means that the mean of our sample is 1.43 standard errors away from the mean. We said that the probability that we got a sample that is more extreme than 1.43 times the standard error away from the mean, which would be a sample here and here, is, let's say, p equals 0.05. And we say that this probability is the p-value. How do we find this probability? The way we do it is that we considered the test statistic, i.e. the number 1.433, not as a number, but as a variable, let's say z. And what we would like to do is we would like to draw a graph which would represent the distribution of z. In other words, it would represent the function of the probability of getting a specific z number. Now, I can tell you that this kind of graph is called the z distribution, and it is a normal distribution. In other words, it has all the properties of normal distributions. For example, it has a line of symmetry that would cut the values of z into two halves. And if you think about it, z, which is the test statistic, can be any number. It could be 1.43, or it could be minus 1.43, or it could be minus 10 or plus 10. So a line of symmetry between all real numbers would go through zero. Now, another property of the z distribution is that we draw it in such a way that getting a number, let's say between minus 1.43 and minus 1.33, is not represented by a value in a y-axis. The y-axis means something different here. The probability of getting a number between minus 1.43 and minus 1.33 is the area under the curve between this interval. We call such functions probability density functions. We have said that if the probability of getting a test statistic less or equal than minus 1.96 or more or equal than 1.96 is 0.05. So the area under the curve between minus 1.96 and minus infinity, and the area under the curve between 1.96 and plus infinity will be 0.05. We have also said that if the probability of getting a value more extreme than minus 1.43 and plus 1.43 is our p-value. And what is our p-value here? How would we represent it? We'd represent it as the area under the curve between 1.43 and plus infinity and minus 1.43 and minus infinity. So if this area here, which we call our p-value, is more is larger than 0.05, then we know that our sample does not belong to what we call extreme samples. It belongs to the 95% of the population. Why is this important? This is important because in statistics, we assume that because it is very unlikely that we have got a sample so extreme that it belongs to the 5% of the population, we assume that what we got is not a sample that belongs to our population, but a sample that belongs to a different population. But there is a probability we are wrong, because we know that there is a 5% probability that we get an extreme sample. We can't just say if we got an extreme sample, then that doesn't belong to our population. It's unlikely, but it's not impossible. So if we say that a sample that looks extreme does not belong to our population, we may be wrong. And what is the probability that we are wrong? Well, the probability of getting an extreme value is 0.05. So the probability we mistakenly say that an extreme value does not belong to the population is 0.05. In other words, the probability we make the error of telling are very tall, or here are very tall, or are very short friends that are not part of us is 0.05, and we call our error a type 1 error.